Hello, my name is Chris Vernon. I'm a senior data scientist at Pacific Northwest National Laboratory, and I would like to take a few minutes to talk with you about GCAM and Demeter, a global integrated human Earth systems perspective to modeling land projections. We're going to use GCAMwrapper with Demeter to conduct a two-way, highly coordinated coupling to update crop yield assumptions on a per time step basis in GCAM. At this time, I would also like to acknowledge my co-author, Pralit Patel, who is the lead developer for GCAM and GCAMwrapper. Let's start with a little background. Researchers and decision makers are increasingly interested in understanding the many ways in which human and Earth systems interact with one another at scales from regional to global. For example, how might changes in population, income, or technology development alter crop production, energy demand, or water withdrawals? Or how do changes in one region's demand for energy affect energy, water, and land in other regions? Well, this session will focus on two models, GCAM and Demeter, that provide capabilities to address these types of questions. This tutorial will introduce GCAMwrapper, which is a Python wrapper for GCAM, to provide hands-on walkthrough for a reference case so you can become familiar with configuring and running GCAM and Demeter while having the ability to update GCAM's parameters on a time-step by time-step basis. Our goal will be to demonstrate how to integrate GCAM using its new Python wrapper into existing workflows that research energy, water, land, climate, and socioeconomic dynamics to provide a global human Earth systems perspective. We'll be using today a Jupyter Notebook environment to conduct this tutorial. It's been provided by MSD Live, which is a multi-sector dynamics resource that provides computational data and software support. It is continuing to emerge, and we thank them for hosting this today. All of the software we use today is available in our GitHub project for GCRE, and those links are present here in the top of the browser. For an overview of the experiment today, we're going to give you a little background to show that we're going to attempt to incorporate climate-induced yield impacts in GCAM on a per time step basis. So to do so, we're going to utilize an archive of global gridded crop model results that have been published as part of the GCIMS project. Now, although this exercise has been conducted before in a few publications, a shortcoming has been identified in the design of these experiments in that they assume a fixed spatial distribution of crop production that is used to weight the gridded yield impacts. So other similar studies have also indicated this missing dynamic can create significant bias. So we're going to use the GCAM Demeter coupling to address this insufficiency by updating the spatial distribution of cropland to evolve with future scenario conditions. This is what we're going to try to do, and we want to note that we do apply simplifying assumptions to ensure that we can do this computation in a tractable way for illustrative purposes. Our outline for this experiment will be to load and initialize GCAM through its calibration years, and then take a look at some of those regional projections. We're then going to use Demeter to actually downscale GCAM land use outputs to 1/2 degree resolution. Now, this does match the resolution of the GCIMS crop yield data as well. Then we'll run and query the first projected GCAM year without those climate impacts accounted for, and to create a baseline for comparison. Then we're going to load GCIMS yields and apply weights using Demeter's gridded crop downscale data. Update will come next to the adjusted yield impacts, and then we're going to rerun the first projected scenario with climate impacts and then compare the results finally. So let's get started in the code. I'm going to import the packages, but I do want to note as we do this that GCAMwrapper is imported as GW, or an alias to that. Also, Demeter imports its model class and the full body of the package as well. But you'll see this GW throughout. That just is an alias referencing the GCAM wrapper package. So using GCAM wrapper, let's start by taking a look at some of the documentation that is contained within the functions and classes itself. Most importantly is this GCAM class. Take a look here. And we can see that this class is actually a wrapper around GCAM itself to interactively run scenarios and do get, set, or updating of parameters throughout each time step. The methods that exist within this particular class we'll see throughout as well, and they do things like convert period to year and get the current period of the run, get the current year, and so on. So let's go ahead and step through some of this and load up our GCAM specific files. These are the GCAM executable and the configuration XML. If you're familiar with GCAM at all, many of you will know about those files. Next, we're going to instantiate GCAM. So this is the class we just viewed help on, and we're passing the XML file as well as the executable and creating an instance of GCAM. All right, we now have an instantiation complete and all the input files have been parsed and GCAM is ready to start. The next step for us is going to be to run the model through its calibration years through the base year of 2015, which is the base year of GCAM. I'm going to go ahead and execute this. Here you'll see these methods that we spoke of previously coming into play, where we convert year to period. So instead of just using the period as is normally represented here as period 0, 1, 2, and so on, you can actually call out that period using an integer 4-digit year. And then you can run the period with this method. The API for this is fairly clear and easy to understand. And so while this is running and now we have it complete out through 2015, we can kind of move along. All right, next, let's query out this land allocation data. And we're going to do this by using get query. So this is a wrapper around a fairly complex portion of what has existed previously with XPath-like queries to get information out of output GCAM XML databases. So this really clears up a lot of the intricacies that you have to learn to be able to extract information from GCAM from a pure query perspective. We simply say we want land and land allocation, and then we give it our parameterization, which is, in this case, we want all regions, all leaves, and the year less than or equal to the current year that we're running. This get data method allows us to retrieve that information and store it in a pandas data frame, which you can see here is pretty standard if you've worked with GCAM land data before. This is what you would generally extract out. It's good to note as well that we don't need the whole output database from GCAM anymore to extract information on a per time step basis. So this is really handy in reducing the overhead of keeping data. Moving on, let's visualize some of what this looks like from a regional perspective in GCAM. So if we take a look at loading first into our Demeter formatted data frame, preparing for that Demeter run in a minute. Let's see here. Here we have GCAM land allocation by region. And so this is coming directly from our GCAM output. And we're just kind of taking a look at some of the summarized results here. Here we have total land allocation by region for combined corn, meaning corn irrigated and rain-fed designations all combined, as well as corn allocation specifically for the CONUS and where that exists within the GCAM land regions. Here we have for the globe, corn allocation for all the global basins for 2015. And now I believe we're ready to run Demeter. So we have our GCAM 2015 step taken care of and the land allocation pulled from that specific run. Now we're going to pass that information to Demeter, which we've just instantiated. We are going to initialize Demeter and get it set up and ready to go. And now we're going to actually run process step, which runs the current time step of 2015. And so this is the part of Demeter that applies intensification and extensification to be able to downscale those regional allocations of land onto a gridded surface. And so Demeter will process this, and then we will rejoin and move to the next step. Okay, Demeter's all finished up. Let's go explore some of the downscaled outputs from Demeter. All right, we're building our geodata frame, which is a georeference data frame for use in generating these plots from Demeter's results. Here we show now, instead of the regional allocation of land, a gridded representation of, I believe this is crop to, so corn, for irrigated and rain-fed crops. And there seems to be where we would expect. And then if we check out forest and the gridded representation of forest for the globe, again, kind of what we would expect to see there. Let's just clean up Demeter, get rid of the logger, and move to our next portion of this experiment, where we actually run GCAM up to the period of 2020 without yield impacts. So what we're doing here is creating a baseline to compare against when we run with the yield impacts, where we incorporate what Demeter just produced to update that data. So we'll let this finish and rejoin in just a moment. All right, our Demeter, our GCAM run is all finished up to period 2020. So now let's take a look at some of those results. Again, these are without accounting for yield impact. And so we are just getting these as a baseline right now. Again, utilizing our get query, get data calls and methods from GCAM wrapper, and making this very easy to construct these query strings. Now we're going to go down and actually start generating some of the yield impacts and applying those scalars to the EasyMIP data. So let's do that now, where we use Demeter downscaled outputs to build crop yield scalars. So now we'll actually apply this yield scalar to the EasyMIP data. These are coming out as pandas data frames, which are easy to maneuver. And now that we have our new yield scalars applied, we can go ahead and update GCAM's parameters. And so let's go ahead and fire this off. And at the same time, we're generating a new run of 2020 with the climate impacts accounted for. So our query parameters now have changed a little bit. We're using this add sign to actually set our data. And here's this call here. So we define our query for agricultural yield and set up our query parameters, and then call the set data method, which actually updates that and readies the next period, for which we run here with the run to period method. We have updated GCAM at this point, and we're going to look at the results with impacts for comparison against the baseline that we generated. Make sure this one finished, and it did. Now let's compare 2020 GCAM outputs with and without crop yield updates. The first one that we're going to check out here is the corn producer differences in prices by regions with and without considering the impacts. And let's take a look here. We do see that there's quite a bit of relative difference. I can raise this up a bit for each of these regions. So we're seeing that our updates actually are making an impact and the outcomes on a, again, even a per time step basis. We would expect this to keep amplifying as we progressed into the future. And this cycle that we're doing now would be repeated all the way through the end of the century, where we're transferring data from Demeter or from GCAM to Demeter and then back to Demeter and then moving to the next time step until we reach the end of the period. Here we have the difference in corn domestic prices by region with and without considering the impacts as well. Again, a noted difference in domestic prices from a relative perspective. We're going to check out the difference in corn yield globally with and without considering those impacts and see where those geographically are really becoming prominent. And you can see in both of these for irrigated corn and rain-fed corn, there's a lot of regional influence here where changes are taking place. As we move down to take a look at corn production globally, we'll see again, both for irrigated and rain-fed corn, regional impacts coming into play. So hopefully today we've provided you with a high-level demonstration of how to integrate GCAM using its new Python wrapper into existing workflows that research energy, water, land, climate, and socioeconomic dynamics to provide a unique and global perspective for human Earth systems science and research. As always, please feel free to contact both myself and Pralit if you have any further questions. And as always, we'd like to acknowledge our sponsor, the U.S. Department of Energy's Office of Science, as a part of research in multi-sector dynamics, Earth and Environmental System Modeling Program, and the Pacific Northwest National Laboratory for supporting this contract. And all views and opinions expressed in this tutorial are those of the authors. Thank you, and hope you have a great day.